Hi everyone, this is the chapter 4. We're going to start with the flexible pavement design chapter, which is now the reference for this chapter is the pavement analysis and design second edition by Huang. So let's get going. Today's learning objective, we're going to try to first cover a simple introduction on the basic definitions of pavement analysis and design, what I mean by pavement analysis and what's the difference between pavement analysis and pavement design. And then we're going to list the three different types of pavement structures that we typically use on any roadway. And then we're going to explain how pavement does fail and what are the conditions failures that we typically see in any road, and then we're going to identify some of the basic differences between flexible pavement and rigid pavement. So, as an introduction, early hot mix asphalt consideration, when we started looking into hot mix asphalt back into the history, it started about 100 years ago or so, and the main goal of constructing asphalt pavement roadways was simply to get people out of the mud. The quality of the hot mix asphalt wasn't a major issue. If a mix would work fine in one state, they will just implement it as is if, to another state until they figure out there's something wrong and then they need to change. But the mix design concepts were very simple. The amount of traffic back then were also very low. Therefore, again, it was just a trial and error at the beginning as the first stage. When I say pavement, by definition, pavement is the upper layer of a roadway or airport or parking area structure. So any man-made layers, all the layers on top of the soil, this is what we call a pavement structure. So as I said, it includes all the layers resting on top of the original ground, and it consists of all the structural elements or layers, including shoulders. So typically for hot mix asphalt, we have the bottom layer, which is on top of the soil, we call it subgrade, and then on top of it there is a sub base, and then there will be a base all the way to the top, which is the hot mix asphalt. When I say a design, when I say pavement design, basically this is the conceived or the developed plan for something to serve specific function. So pavement design, we're going to design pavement for a certain thickness, for a certain strength, to handle a certain amount of traffic, as well as a certain amount of climatic condition. So the major difference between a pavement design and pavement analysis, as a pavement designer, you're going to solve for thickness. You are required to know what's the minimum amount of thickness to carry certain amount of loads under materials and environmental condition. While for a pavement analysis, this actually now solves for the condition of the pavement, and pretty much you're trying to predict the long-term behavior of that pavement. So if you're starting a brand new road, you're going to try to design the pavement. So you're going to come up with how many layers you want to have and what's the thickness for each layer. That's what I mean by pavement design. Pavement analysis, this is more or less an existing structure where now you're trying to analyze the structure, especially if I have a premature failure. So you're interested to know or solve for the stresses and the strains at certain points along the pavement structure to know what's the major reason for that failure. Some of an interesting fact about pavement design versus other civil engineering structures, most of civil engineering structures, they do either fail immediately or last forever. So fail immediately sometimes, again, if the bridge is not designed right, if there's not air or wind consideration to go through the bridge, sometimes it would fail drastically in seconds or minutes, like the Como Bridge in Washington. Or it can last forever, like water reservoir, water dams. They are designed to last for 50 or 100 years. The only structure in under civil engineering infrastructures that take time to deteriorate is the pavements. Pavement structures deteriorate gradually over many years, and um, this is the failures basically because of the material deterioration. The quality of the material will decrease with time, the amount of traffic loading, the repetitiveness nature of the traffic loading, as well as the environmental will influence the pavement to fail gradually. So pavement design should be capable of predicting those long-term performance of the pavement, and not as a sudden failure, but a slow progress towards failure. This is here a picture where how pavement performance over design life is all about. If you're having a correct design, you're going to end up with the line in the middle, which is this is the correct design. You're designing it to last for a certain amount of years. The y-axis here, what we call the serviceability, or the goodness of the structure, or how strong is the structure, and the y-axis, this is the years of design. And this is the terminal serviceability, or this is now the failure criteria. I would like this sample or this structure to fail, let's say, after 20 years. So if you're having an exact correct design, this structure should last or should deteriorate gradually until it reach failure at 20 years. If you are over designing it, that means you're having too much materials, the thickness is too much, you are investing too much money compared to what you're supposed to be. Nothing wrong about it, but that means you're going to run out of money to construct other roads. And this is going to represent the purple color here, where the structure is at the serviceability, at the design life, let's say at 20 years, it's still going to have some life into it. Again, nothing wrong about it, but considering you're going to build a huge network or a city, this is an over design. While the worst case scenario that you really want to try to avoid as a pavement designer is to under design, which is the orange line here, where the structure now is too weak or too thin, that the structure now is going to fail at this point, which is, let's say, 15, 16 years instead of 20 years as a terminal or design life. So your goal is always trying to be around this blue middle line, where to serve the exact design life that we needed to last for. So as I said, again, it might not sound logical, but this is what it is. Pavements are designed to fail at certain time, though not right away. So a little bit of history behind the development of hot mix asphalt. As I say, the pavement engineering field as a whole is still in its infancy compared to other scientific fields and engineering. So before 1920s, pavement thickness was based on experience. People didn't know why we put 4 inches instead of five. Same thickness was used for highway sections across the board, regardless of the soil type, which is not true, and we got to know that now. If I'm designing a roadway on top of a strong soil, I would need a thinner section compared to if I have a soil that is very weak, I'm going to end up with a thicker section to adjust for how good or bad the soil is underneath the structure. We also have various methods for determining the required pavement thickness that were developed with time by different highway agencies. For flexible pavements, again, it's all about bituminous materials as well as granular materials. What do I mean by this? Any flexible pavement structure, it has bitumen or asphalt, which is a byproduct from a refinery, the oil refinery process. We mix it with aggregates or crushed aggregate rock or rocks. So typically, the aggregates will be about 95% by weight of the overall mix, and 5% or so will be asphalt. In 1870, this was the very first asphalt roadway in the US, and that was in New York, New Jersey. In 1876, 6 years later, we started to see what we call nowadays hot mix asphalt, but back then it used to be called sheet asphalt pavement, was laid in Pennsylvania Avenue in Washington, D.C., still there. In 2008, which is again almost more than a century afterwards, we have currently about 2.7 million miles paved in the US. The majority of them are asphalt surface. Remember this number, 2.7 million miles, because we're going to compare it to the rigid pavement, which is significantly lower used in the States compared to the flexible pavements. Flexible payment methods, again, lots of methods has been developing over the years. The first method was empirical method, meaning that it all depended on experience, and no one knows why this mix worked, and they just keep repeating on fine-tuning with time until they reach the best design method. But with time, they came up with another methods we're not going to indulge in them in this lecture, but they typically cover them later on. limit shear failure method, which means asphalt can fail because of shear failure. Limiting deflection method, if we have the asphalt pavement will deflect a certain amount, that's gonna consider failure, and therefore we need to design the pavement not to reach certain amount of deflection or certain amount of failure, a certain amount of shear. Regression methods based on the performance, as well as the very last and up-to-date methods is what we call mechanistic empirical methods, meaning that it's somehow halfway is empirical, but the other half is mechanistic, which is now highly dependent on the physical components of the mixtures and how can we measure true stresses and strains in the pavement structure. Rigid pavements, however, which is what we call PCC, which is Portland Cement Concrete. The very first concrete pavement was Fontaine in Ohio. This was in 1893. And then again, a century later, we have 52,000 miles worth of rigid pavements. 52,000 miles, comparing it again to 2.7 million miles worth of asphalt pavement. So again, you can see a huge difference. The design methods, when it comes to the Portland cement concrete, they didn't change much over the years simply because asphalt um, is a viscoelastic material. It has lots of variability, and we're still fine-tuning the design compared to concrete, which again doesn't really depend on the speed of the vehicle or doesn't depend on the temperature. It's the performance is pretty consistent. And the main factor for Portland cement concrete design is mainly the flexure stress um, consideration. When it comes to classifying pavements, so classification of the pavement, we can classify them based on the function or based on the structure. If I want to classify pavements and based on the function, I have pavement structure and airports. We call them airport pavements. We have highway and freeway pavements, and we have parking and local street pavements. When it comes to the if I want to classify pavements based on their structure, I have rigid pavements. I have flexible pavements, which is asphalt concrete. I have composite pavements, which is again one layer would be hot mix asphalt on top of the PCC or vice versa. Or I can have a gravel or unpaved pavements. Another type of classification is again I can have flexible pavement, composite pavement, or rigid pavement. For flexible pavement, I can have either conventional hot mix asphalt or full depth hot mix asphalt. And I'm going to explain this in a little bit. When it comes to rigid pavement, I have three types of rigid pavements. The very first one is called jointed plain concrete, JPC, and the second one is jointed reinforced concrete. As you could tell, some reinforcement in this type of structure, and continuously reinforced concrete. And this is where now we have much more reinforcement in this rigid pavement. Or I can have somewhere in between, which is the composite section. Composite section, this is now a mix between hot mixed asphalt and PCC. I can have a black topping, meaning that I can have a hot mixed asphalt, and then beneath that there will be a PCC layer, or I can have a white topping where the PCC layer will be on top, and underneath that there will be a hot mix asphalt layer. When it comes to flexible pavements, mainly there are two schools of thoughts to design flexible pavement. I can have conventional flexible pavement or full depth flexible pavement. The conventional flexible pavement, as you could tell here, we are depending on every single layer. We have multiple layers on top of the natural subgrade. You would compact the subgrade, which is typically we would compact the top 6 inches, and then I'm gonna have to depend on a sub base and a base layer. Those are gravel, crushed aggregates, and then typically the subbase is somewhere between 4 to 12 inches. On top of that, there will be a base course, which is 4 to 12 inches. And then I'm going to have two major asphalt pavement layers. The bottom one we call it the binder course, which is ranges from 2 to 4 inches, and the wearing course 1 to 3 inches. And we have different types of coats. We have a prime coat, we have a tack coat, we have a seal coat. And I'm going to explain each one of those in a little bit. But the difference between the conventional mix and the full depth, as you can see here, for the full depth, we really have a natural subgrade, we prepare it, we compact it, and then the whole structure is based on multi layers of asphalt mixture. That means there is no asphalt, there is no aggregate bases or sub bases. It's all asphalt mixture. Typically, the full depth one will be more expensive, but it will last longer compared to the conventional mix. Back to the conventional mix, we have a prime coat, we have a tack coat, and we have a seal coat. What's the difference between the three of them? Before we get into this, I need again to explain the seal coat. The seal coat, which is on top of the structure, this is after we pave. It's a thin coat of liquid asphalt and spread of aggregates. Typically, we try to apply it so it will lock the surface. It will have a water-resistant surface. The water is not gonna penetrate through the surface. Then I have again a wearing course and a binder course. Those are the two asphalt layers that I just mentioned here. We have a wearing course and a binder course. You may wonder what's the difference between the two. The wearing course is this is the top course asphalt pavement. Usually, again, it's a graded hot mix asphalt. It resists distortion under traffic. It provides a smooth surface and a skid resistance riding surface. And typically also is waterproof, especially if I apply a seal coat afterwards. And it protects the pavement as well as the subgrade. The binder course, this is the HMA too thick to be compacted in one layer, so larger size aggregates for example, for Nevada DOT, compact maximum of 2 inches lift at a time. So the binder course, or any other asphalt sample, any other asphalt layer. If let's say you come to design the binder course and you say 6 inch, I cannot compact a 6 inch asphalt layer at once. We compact them as lifts. Every lift is the 2 inches, maximum is 2 inches. So if you're designing 6 inches, you're gonna come 3 times, 3 days, you're gonna apply the first layer 2 inches, compact it, and come second day, apply another lift, and third day the third lift to achieve the overall thickness. Tack coat is the asphalt emulsion. It's an asphalt emulsion diluted into water. The main goal for the tack coat is actually to bond between surface being paved or overlaying course, and it's very thin. Typically, it's uniformly cover the entire surface. The prime, so typically the tack coat, by the way, is between different lifts. Let's say again back to the example, if I have a 6 inch hot mix asphalt, and those 6 inches, I'm gonna have 3 lifts. So in order to have the 6 inch layer, in order to see it as a one structure, although we're gonna have them as 3 different lifts, we apply the tack coat between each one of those 3 different sub layers. The prime coat though is different. Prime coat we apply it just before we start to pave. We apply it on top of the aggregate base course. So what we do with the prime coat is low viscosity cut back asphalt. It's applied to an absorbent surface to lock all the air voids and that asphalt and that aggregate base just before we pave. So really the major difference between prime coat and attack coat is as follows. Prime coat, again, it penetrates into the underlying layer and plugs the voids and form watertight surface, because again water is enemy number one to any pavement structure. So last thing you want to see is water penetrate all the way to the soil. While the tack coat, this is the tack coat now, the coat that we apply between asphalt lifts or asphalt sublayers, so it doesn't require the penetration of the asphalt into the underlying layer. Another note here for structural analysis purposes, the wearing course and the binder course are combined into one layer unless if they are composed of 2 different materials. So if you're doing a design and you're running, let's say, as a software to design the pavement, you're not going to put 3 different lifts. Each lift is 2 inches, or even if I have 4 inch binder course and 2 inch wearing course, you're going to put it all as one layer, because you apply the tag code, which means all the sublayers are going to act as one. Except again, if the wearing course and the binding course have different mix designs, then you're going to assume that these two are different structures, and you need to submit each one of the layers as a different structure. How about seal coat? Seal coat is layer thickness is neglected. Typically, it's less than 1/4 of an inch. and it's not a structural layer, therefore we do not consider it in any pavement analysis and design. For rigid pavements, we have mainly a base course or a sub-base course on top of the subgrade, and then we apply on top of that the Portland cement concrete slab. It's an optional layer because, and on rigid pavement structures, we mainly depend on the PCC slab to handle most of the loading, which is different conceptually compared to the flexible pavement, where we depend on every single layer between the asphalt layers and the base and the sub-base to hold some of the loading. For the PCC, most of the loading is handled by the PCC slab itself, yet we still like, mainly contractors like to have a base course layer to do multiple things. It can control pumping mainly, basically if you ever drove on any roadway and you see some fines on the sides of the shoulder or even on the main street itself, those fines basically the water gets inside the surface of the structure, go all the way down, and then now if I have two layers or two slabs adjacent to each other and the water gets into, and once we keep applying traffic loading on them, water is gonna pump the fine materials from the subgrade all the way to the surface, and that's why I call it pumping. So if I have a subgrade only beneath the PCC layer, and if there's any crack in the PCC layer, I'm gonna have the pumping problem. That's why having a base or a sub base is gonna prevent that from happening. It also controls frost action. It can be a good drainage layer. I can also control shrinkage or swelling of the subgrade by having a base layer, and it's a good construction platform. It's much better to pumping concrete while having the reinforcement before we have reinforcements before we pumping concrete. So if this reinforcement or the rebars are not attached well in a base layer. And if I decide not to have a base layer and attach this reinforcement into the soil itself, once I pump in concrete, sometimes those reinforcements will move. So contractors like to have a base layer to have a good base for the rebars before we pump in concrete. Rigid pavements, as I say, there are three main structures. Under rigid pavements, we have jointed plain concrete, which are closely spaced joints. They have very minimal reinforcement. They can be with or without dowel bars. We have the middle one, which is the jointed reinforced concrete, JRC. This has some steel reinforcement. Therefore, once you have more reinforcement, you can have a longer joint spacing, and we have dowel bars required for this structure. And the most and highly sophisticated rigid pavement is the continuously reinforced concrete, which is now I have full steel reinforcement. There's no joints because now it's full reinforcement. It's very similar to designing, for example, slab in any structure, and it's prone to transverse crack though because it's a long structure and there's no joints in the middle. This is here a picture example for the jointed plain concrete, JPC. This is again very minimal reinforcement relatively speaking to the other two types of rigid pavements. Um, the length of each slab is maximum here 15 feet. Again, it cannot be any longer because there's not much reinforcement to hold it together. So that's again typical joint spacing, as I was saying, 12 to 20 feet at the most. What happens for jointed plain concrete? We have to do what we call a saw cut joints. Basically, what happens after we pour in concrete in order to um, minimize random cracks, we apply a saw cut joint, which is actually what I like to call it a man-made crack. So with certain after a certain amount of time after pouring the concrete, again typically the window of doing the saw cut somewhere between um, 12 to 48 hours. If you wait too long, the concrete is going to shrink by itself and it's going to have cracks all over the place. And if you do it very early, the concrete doesn't have enough strength to apply a socket joint on it. So typically what happens again, the right window timing, we're going to apply this socket joint, as you can see here, the width, I mean the depth of the joint somewhere between 1/10 to 1/4 of the overall thickness of the PCC layer. And sure enough, minutes, if not even seconds after you apply the joint, you're gonna have a crack developing all the way to the full depth of that PCC, which is fine. Again, this is a man-made joint or a man-made crack. It's a location where all the stress concentration will go through this point instead of having multiple variable random cracks all over the place. Jointed reinforced concrete, which is again, this is now we can see more reinforcements in such structure. We have now three different types of structures. We have the tie bars, which ties two adjacent slabs, and we have dual bars. So this is on the longitudinal direction of the traffic, and we have also what we call the welded wire fabric, WWF. This is the welded wire fabric mesh to again, to make sure that we're not gonna have transverse crack or random cracks. So the typical joint here, once we apply all these types of reinforcements, now we have up to 50 feet joint length or joint spacing instead of maximum 15 to 20 feet. The jointed reinforced concrete, again, the whole concept of having reinforcement, as you could see here, this is to have a better load transfer. So if I have a plain concrete and there's an open crack, the wheel, this is the W wheel, one of the wheels of any vehicle. If I'm getting closer to that crack, what happens is this slab, which is the loaded slab, is going to feel the entire amount of this load. And what happens, the water can get into here and it's going to pump up all the fine materials to the surface. While if I have some reinforcement, as you can see in this picture here, this is a reinforced pavement. Now I have a crack, but that crack is closed. Therefore, this slab and this slab here is going to feel half of the weight of that wheel. So let's say that wheel has 2,000 pounds. This part is going to feel 2,000 pounds, and the unloaded part is going to feel another 2,000 pounds, simply because we have reinforcement and there is good load transfer between the two sides. Now, this is the continuously reinforced concrete, which is now fully reinforced, lots of reinforcements, longitudinal transverse directions. Yet again, you would still see typical crack spacing somewhere between 3.5 and 8 feet, but those are map cracks, very small, then not a big problem compared to if I don't have any reinforcement, where I'm going to see a much bigger types of cracks. But as you could tell, there is no joints here except if you have construction joint when you stop a day and you start the second day. But other than this, it's a continuous structure simply because there's lots of reinforcement, which is going to allow us to have a very long, infinite sometimes length of the continuously reinforced concrete structure. When I said about this, I mentioned this before. When I said about the composite pavements, we have a black topping or we can have a white topping. Again, black topping, which is typically AC on top of the existing PCC surface, or the white topping, which is you can have a hot mix asphalt at the bottom, and then the Portland cement concrete on the top. Well, now after we have some good amount of introductory information about pavement engineering and looks like two types of pavement structures I have, and now the pavement does fail. As we all drivers here, we drive from one place to the other place, and we see pavements. Sometimes they are good pavements, sometimes they are failing pavements. So asphalt does fail, and pavement failures, they can be categorized under two um, reasons. The first one is we call it a structural failure, and the second one is a functional failure. Structural failure, as you could tell, is a breakdown of one or more of the pavement components. If the hot mix asphalt is failing, or the sub base, or the base, or the soil is failing, that's a major failure, and we call it a structural failure. Whereas functional failure is now this where when what will happen and when you are unable to carry out the intended function without discomfort, high stress on motorists, or safety problems due to roughness. So it's all about your driving comfort. How rough is the road? Is it too rough? Or sometimes the other extreme, is it too smooth? And if it's in a rainy condition, are you losing control over your vehicle? that's also a functional failure. So functional failure may or may not be associated with a structural failure. So, but those are the two major types of failures that we typically see in any payment structure. So let's talk about asphalt payments first and how do they really fail. The four major problems that we do see in any flexible payments, the very first one is this picture right here. This is the fatigue cracking. So we call it high severity fatigue cracking. Fatigue cracking basically it's similar to if you go to the gym and you hold a dumbbell of that's 10 pounds. You keep exercising maybe for 10 15 minutes, it's nothing. After 15, 20, 30 minutes, the same weight that you were able to hold, now you can't anymore. What happened? It's the same weight, but you are fatigued. You are getting tired. Same thing happens to flexible payments actually. So because we are having a repetitive nature of traffic loading on any roadway, especially interstate system, what happens is with the repeated loading, we typically have this type of fatigue cracking. Besides fatigue cracking, we also have what we call the permanent deformation. Permanent deformation is what we also like to call rutting, which is the deformation in the wheel path. If you ever driven on a roadway when it's raining and you see the water is in the wheel path, typically that's what we call rutting, which is deformation in the wheel path because of repetitive loading. Um, it's a problem that's highly significant in rainy condition where we can see the problem or the issue of hydroplaning, which is when you drive on a rainy condition and there's water like this, the wheel you will be driving on a very thin film of water. That means there's not much interaction or friction between the tires and the roadway, and that's a very hazardous situation. The third problem that we also see in any flexible pavement is transverse cracking. Transverse crack is a crack that you could see again at the bottom left here. This is a crack that's transverse or 90 degrees to the traffic direction. Typically, it's cold weather because it's cold weather, so the asphalt there will be an amount of tension, stresses and strains inside the asphalt. And asphalt is not good to handle tension. It's good at handling compression. So with time, once we maximize the amount of tension inside the asphalt pavement because of the temperature, the variation between daytime and nighttime, this is when we start to see transverse cracking. Potholes is also if you ever again, everyone knows them. It's a hole in the pavement that you can see the pavement now is sinking, or some of the pieces is leaving the structure. This happens mainly on the sides of the roadways because when we pave, the paver that has a shoulder, which is it's like or wings. So when we pave, sometimes the most of the paving weight of that paver on the main structure and the size of the roadway or the size of the outer size of the lanes are not highly compacted, and therefore if the pavement spot is not highly compacted, it's gonna create a spot where there is high amount of air voids in them. So once it rains and with the repeated loading, you're gonna see the potholes start to originate at those locations. So those are the four major parts, four major failure forms that pavement can see. For rutting can happen because of two main things. Rutting can happen because of failure in the top layers, which is the hot mix asphalt layer, or it can happen due to the failure at the soil layer. So the only way to know what type of rutting you're gonna have, you need to do what we call a trench study, which you see in this picture here. You need to cut through and see whether this rutting is coming from the surface or the bottom layers of the structure. So, in summary, we can generally say that flexible pavement have three major problems: rutting, thermal cracking, and fatigue. Rutting is most critical at high temperature. Fatigue is most critical at moderate temperature, and thermal cracking is most critical at low temperature. When it comes to rigid pavement does also fail, and some of them are similar to flexible pavement, and some of them are very unique types of failures to rigid pavements. So the very first one is the transverse cracks. The transverse crack again are similar in the shape or form that we see in flexible pavements. Again, because of not having enough reinforcements or the late sewing. Again, we talked about the joint sewing. So if it's not cut at the right time, excuse me, if uh, if the contractor doesn't cut the joints at the right time, we would see this crack right there. Sometimes again, if they wait like more than 2 days, the crack will initiate already. Still, as you could see, the contractor came and did his job regardless, which is again, it's too late. But the crack happened because of late sewing, or sometimes it's poor construction technique or poor construction quality. If the materials are not strong, you will see that problem. If the construction technique, again, we're not paving or we're not compacting all the locations at the same amount of compaction, we also would see that issue. Other problems for rigid pavements, we see pumping, we see corner breaks, we see folding, all the way to joint spooling. Pumping, as we talked about it earlier today, again, this is pumping where we see fine materials getting pumped from the bottom of the subgrade all the way to the surface because of water infiltration. Water will get into the structure and then it's going to pump all the fine materials to the surface. And that is considered a failure because with time, once we lose so much of that fine materials at the bottom of the PCC structure, the whole PCC structure will have what we call faulting, which is one layer or one slab will be higher than the other, and that's also a problem. Or I can have a corner break, something like that, or I can have a joint spalling. The worst case scenario you can see is the blow up, which is or buckling and rigid pavement. So this can happen because again, if it's not fixed right, if the joint reinforcement are absent, or if there's bad construction practices, you can have such problems. So in conclusion, the main differences between flexible pavements and rigid pavements are as follows. When it comes to materials, they are different. For flexible pavement, it's all about asphalt as well as crushed aggregates. When it comes to rigid pavements, we use Portland semi-concrete, water, and aggregates. For load distribution, as you can see, flexible pavement distribute the load in a small area. Therefore, that's why we need multiple layers between subgrade, between a subbase and a subgrade, subbase and a base to distribute the load on a bigger area until we reach the soil. Whereas for rigid pavement, it's a very strong layer. It takes most of the load and distributes it very well to the bottom layer. But when it comes to life cycle cost is a key thing. For flexible pavement is very considerably cheaper than rigid pavement as a startup cost. But we know flexible pavement um, will tend, at least historically speaking, will have more um, rehabilitation and maintenance with time, much more than rigid pavement. So that's why here you could see the flexible pavement. If you extend this line here, we're gonna have more cost over the time for flexible pavement to fix it compared to the rigid pavement. Although nowadays, in the past 10, 15 years, we're having additives to the flexible pavement such as asphalt rubber, fibers. The gap in life cycle cost between flexible pavement and rigid pavement is getting very close. This is here a tabular form of the differences that we talked about. Again, load distribution for flexible area is wide area, relatively speaking. Rigid pavement is distributing it to a much bigger area. That's why it's a wider area. This is bituminous surface. We have your concrete surface. And the list goes on all the way to, again, higher maintenance cost for flexible pavement, where here and rigid pavement is very minor variation. Subgrade strength have little influence on the structural capacity. So with that, again, I hope you're not going to design any pavement that's going to have a little lake that you can fish from, as you see in this picture. With that, again, we finished the introductory part of this chapter, and we will see you next time when we talk about how we do the structural flexible pavement. Thanks so much. Bye-bye.